These are your notes for section 7.2, natural base of e. Determine if the model represents exponential growth or exponential decay, and then find the initial amount and the percent increase or decrease. So looking at this, we can tell if it's growth whenever our base is greater than 1, decay when it's less than 1. This is 1.2, that's greater than 1, so this is going to be growth. The initial amount, remember, it can be written in the form y is equal to a times some base to the x power. Our initial amount is at a. If there's nothing out there that's multiplying by it, then our initial amount is 1. And our percent increase or decrease. So 1 is 100% for your base. So 1.2 minus 1, that'd be 0.2, changing from a decimal to a percent, move our decimal place 2 places to the right. That's a 20%, and it is increased because that's above 100. Our next one, 0.78 to the x, that is less than 1, so that's going to be decay. Still doesn't have anything multiplied by it, so your initial is 1. And here we're going to do 1 minus 0.78, which is 0.22. Move it 2 places. That's 22%, and that is a decrease because it's less than 100%. 5/8, less than 1, so that's decay. Initial amount is 1, and 1 minus 5/8 is 3/8, which is 37.5%. Number 4, your base here. This is a nice one because your base is right here is greater than 1, so that's growth. 28 is going to be your initial amount. 1.03 minus 1 would be 0.03, which is 3%, and that is an increase. This was a decrease. Right over here, we've got 0.95, that's going to be decay. Our initial amount is 25. I don't think I put an extra 0 there. So 25,000. And 100 minus, or 1 minus 0.95 is 0.05, which is a 5% decrease. To the x, this is a growth. Our initial amount is 1, and 2 minus 1 is 1, so that's a 100% increase. That a lot of times will confuse kids because they want to say it's a 200%, but you have to subtract that from 1 and then change to a percent. Sketch the graph of the natural base exponential function y is equal to e to the x. Use your graphing calculator and the e to the x key. What are your domain and range? So we're going to go to y equals. Our e to the x key is right down here where it says ln, so you're going to hit second, and then that'll give you that e. Do not try to put in the e from the letters. Use that e to the x. And we're going to make our table first. So at -2, this is 0.135, 0.368, 1, 2.718, and 7.389. Going ahead and graphing it, -2 and 0.135, so it's really close down here. -1 and 3.68, so it's a little bit more up. It should be about a third of the way. 0, 1, 1, 2.7, right in that area, and 2 is at 7.3. It's going to look something like this. Domain. Okay, so we can see it goes in both directions, so our domain is all real numbers. Range. It gets really close to 0, but it never actually gets to 0, so we're going to have a parenthesis 0 to infinity. This is all real numbers. This in set notation would be y is greater than 0. Not a greater than or equal to, just a greater than. Natural base of e. The natural base of e is irrational and is defined as follows. As x approaches infinity, 1 plus 1 over x to the x approaches 2.71828. So that is what e is. So 1 plus a half to the 2, that would be if x were 2. If you had 3, you'd have 1 plus a third to the third. Right here, we're just looking at our exponent rules to simplify this. So remember when we multiply, we add the exponent, so it's going to be e to the 9th. When we divide the coefficient, so 16 divided by 4 is 4, and subtract the exponent, so that's 4e. You could write 4 to e to the first also. 3, we've got to square the coefficient, so 3 squared is 9, and then we have e, our exponents we multiply, so that's going to be negative 8x. Might want to try these on your own. This is e to the 11th, 3e to the 3rd, and 1,000 e to the negative 9x. Natural base functions. So you can have exponential growth if you have e to the x. If you have a negative exponent, it's going to be exponential decay. So looking at these real quickly, you can see, okay, this is a positive exponent, so this is exponential growth. And I would graph these with your calculator. You have 3 e to the x. And again, I use my table a lot on these. Negative 2 is at 0.4. Negative 1 is at 1.1. 0 is at 3. You can see that nice vertical stretch of 3 on that point. 1 is at 8.15, which is off our graph. So that is right there. You can also see exponential growth. It's rising from left to right. F, you have e to the negative 0.5x. That's going to be an exponential decay. So you have y is equal to e to the negative 0.5x. Negative 3 is at 4.4. Negative 2 is at 2.7. Negative 1 is at 1.6. 0 is at 1. 1 is at 0.6. 2 is at 0.3. So it's going to look like this. And this has a nice horizontal stretch. Negative 0.5 is that horizontal stretch. Tell whether the function represents exponential growth or decay. So you might want to try these on your own. This is going to be growth, decay, growth. Again, you're just graphing them with your tables. So 1/2 e to the x. There you get a nice vertical compression. Then the next one, 4 e to the negative x. There's a nice vertical stretch. This one's going to have a vertical stretch as well as a horizontal compression. And what that's going to do, it's going to rise extremely quickly like this. Continuously compounded interest says when interest is compounded continuously, the amount A in an account after 2 years is given by the formula A is equal to your principal e to the rate times time, where time is in years and your rate is a decimal. You and your friend each have accounts that earn annual interest compounded continuously. The balance A in your account after 2 years can be modeled by that function. The graph shows the balance of your friend's account over time. Which account has a greater principal? Which has a greater balance after 10 years? All right, so principal we can see right off the bat because that's this number. So that's $4,500 for your account. and that's also your initial amount. So it's going to be your y-intercept on this graph. So you have a greater principal. You have 4,500 and your friend only has 4,000. Looking at 10 years, so we can kind of estimate 10 years, they're going to be a little bit above 7,000. You can graph this and look at the graphs side by side. You could also just type in 45,000 e to the 0.04 times, this still needs to be in the exponent, your time, which is 10 years. And hit the wrong button, sorry guys. And that's 6,713. So this one's going to be higher. So your friend has a greater balance after 10 years. All right. Number 7 says you deposit $42.50, so that's going to be your initial amount, in an account that earns 5%, that's going to be 0.05 as a decimal, annual interest compounding continuously. Compare the balance after 10 years with the accounts in the previous example. Okay, so y is equal to 42.50 e to the 0.05 x. That would be just a general equation. If you're wanting to look at this specific with the 10 years, you have 4250 e to the 0.05 times 10. And that's 7,000. So it still looks like your friend's going to have more. So this would be in between. In the middle. Go ahead and write your note summary and then work on your online assignment for section 7.2.